Hey guys, today we're going to take a look at gravimetric analysis. So if you remember, when we do an analysis in chemistry, we're talking about separating a whole into its component parts. In gravimetric analysis, the goal is most often to learn what is the percent by mass of a substance in a mixture. So when we're calculating percent by mass, we need two pieces of data. We need to know the mass in grams of one part in particular, and then we also need to know the mass in grams of the whole mixture. And when we divide, we get a decimal number, which then can be converted to a percentage. Now, when I talk about a mixture in this type of problem, the mixture can show up in a number of different ways. For instance, we might be looking at a solution with several things dissolved in it. Here's a beaker of water. Let's say this is water from the Animas River. And we know that it has lots of dissolved ions in it. But if you remember a few summers ago when there was the mine disaster up in Silverton and a lot of extra stuff, nasty stuff, dumped into the Animas River, well, one of those was lead. So let's suppose that you took a sample of water from the Animas River and you wanted to know the percentage of lead ions in the river. Well, that would be an example of a gravimetric analysis problem. You would have to find a way to separate out the lead and then compare its mass to the mass of the whole mixture. Another type of gravimetric analysis might have you looking at a mixture known as an alloy. Alloys are homogeneous mixtures of several metals. So jeweler's gold is an example of an alloy, and you've probably heard of 18-karat gold and 12-karat gold. Well, those are different from each other in the percentage of gold atoms. So 18-karat gold is actually 75% gold atoms, and then the other 25% is made up of other metals, perhaps silver or copper or zinc. And then in 12-karat gold, the percentage of gold atoms is even less. So gravimetric analysis would allow you to take an example of that solution and determine the percent by mass of, for instance, the gold part. Yet another example of gravimetric analysis might be in forensics work. Suppose you had an example of cocaine that was obtained, in a drug bust. And you knew that the cocaine wasn't pure, but instead was laced with impurities. Cocaine is a compound with a formula, but if this sample was known to contain some other stuff besides the cocaine molecules, you might perform gravimetric analysis to isolate the cocaine part and determine what percentage of the drug was that particular part. Now, no matter what type of gravimetric analysis problem we approach, I'm going to suggest that you follow these 3 steps. So after you read the problem, I'd like you to draw a sketch and label as much information as you can. The next thing is to zero in on the part you're interested in and somehow determine its mass. So that's going to require that you separate out that significant part from the mixture. And then lastly, once you have the mass of the part of interest, then you'll divide it by the mass of the whole mixture to get a percentage. All right, so let's take a look at an example problem. If you need to pause the video to copy down this problem, please do. But this problem concerns a mixture that is known to contain barium, among other things. Your sample of the mixture is massed at 3.455 grams. Notice how precise that is. That was massed on a milligram balance. And then the mixture was dissolved in water. An excess of sulfuric acid is added, causing barium sulfate to precipitate out. Precipitate is filtered, washed, dried, and weighed to constant mass. And then we mass that barium sulfate precipitate. And here's our question. what was the mass percentage of barium in the sample? Okay, so this is what we're trying to find, mass percentage of barium in the sample. So again, I like you to start with a sketch because I believe that once you get your pencil to the paper and start putting down something, it engages your brain and you stop being afraid of how complicated the problem is, and you just, you get off the stuck position. So I'm going to start my sketch with just this amorphous blob of the mixture. And I know some things about that mixture. I know that it contains barium and other stuff. And, at this point, I don't know what else is in the mixture, but it turns out that it's the barium part that I'm going to want to somehow separate out so that I can mass it and compare it to the mass of the sample. Okay, another piece of information that I know is that the mixture is massed at 3.455 grams. So that's the mass of the entire mixture. And I somehow need to get this barium part pulled out. When I look at this mixture, there's no way that I can physically take my tweezers and pull out the barium part. So I need some chemistry to do that. Notice the problem says that we're going to dissolve this entire sample in water. So the next part of my sketch is going to show a beaker of water. And once I put the barium mixture into the water, I'm told that it dissolves. Okay, we'll be talking about this a lot as the year goes by, but for now, if something dissolves in water, it becomes invisible to us. All of the particles become uniformly distributed in the water. That's part of the characteristic of a solution. But at this point, there's nothing solid left. So all the parts of the mixture are sort of free floating in the water. Okay, so I may have separated the barium parts from the other stuff, but I don't have it in a way that I can mass it. So yet another step is required. And you're told that an excess of sulfuric acid is added to the solution. So in comes excess sulfuric acid, H2SO4, and that causes barium sulfate to precipitate out. Okay, that's really important. When we add this particular reactant, apparently the bariums in solution find the sulfates which go into solution, and barium sulfate is an insoluble precipitate. Here's my abbreviation for precipitate. A precipitate is simply a solid that appears in solution and it will not dissolve. So I could take a stir rod and stir and stir and stir this solution. This stuff that was formed, this precipitate, is going to stay solid. It's not going to disappear back into solution. All right, so now I have all of the barium that came from the mixture and it got dissolved. Now all of this barium has been trapped in a new compound that has a formula. The next thing I'm going to do is take this whole mess and pour it through a filter that's lined with filter paper. And the filter paper will allow everything to drip on through except the barium sulfate. That solid cannot make its way through the filter paper that lines the filter. So I've trapped this solid that has the barium in it. I'm going to filter it, wash it, dry it, and weigh it to constant mass. And then it turns out that that barium sulfate precipitate has a mass of 0 0.2815 grams barium sulfate. All right, that took a few minutes to do all of that sketching, but I really do feel that's a very valuable step. It allows you to identify what all of the numbers, sort of have a visual of where those numbers belong and what is going on in the procedure. Okay, so now let's move on to the second part of any gravimetric analysis problem. Determine the mass of the part you're interested in. Okay, so I had barium in the mixture. I didn't know its mass. I have moved it over here to becoming a part of a compound that has a formula, and I now know the mass of that compound. So I'm going to start with that 0.2815. Remember to label the unit and the identifier. So I have the mass of that precipitate. And what I really want to know is how much of this mass is due to the barium part. So this is where I use my periodic table. And I come up with this fraction. This fraction is actually the percentage of barium in any sample of barium sulfate. So I am using my periodic table, first of all, to get the molar mass of the compound barium sulfate. Periodic table tells me that I have 1 barium and 1 sulfur and 4 oxygens in a single molecule of barium sulfate, or put another way, the mass of a mole of barium sulfate, 233.39 grams. And out of that mole of barium sulfate molecules, there is 1 mole of barium atoms. Atomic weight of barium is the 137.33 grams. So again, guys, this fraction is the same thing as the percent composition of barium in barium sulfate. My sample of barium sulfate has this mass. Here's the percentage by mass of barium in any sample of barium sulfate. And when I multiply that through, I come up with 0.1656 grams of barium atoms in my sample of barium sulfate. Lastly, I'm going to use the mass of this barium part and divide it by the mass of the whole mixture that it came from. So 0.1656 grams of the barium part divided by the 3.455 grams of the original mixture. And when I divide those very precise numbers, my calculator gives me a whole lot of digits. Okay, 4 sig digs in this measurement, 4 sig digs in this measurement. In my answer, I want to have 4 sig digs. And then I'm going to change that decimal number into a percentage by multiplying by 100. And I get 4.793% barium in the mixture. Okay, guys, I hope that was helpful. Before we shut down, let's just go back and remember that in any gravimetric analysis problem, when you're asked to find percent by mass, you have to first of all come up with a way to separate out the part that you're interested in and then divide that part of interest by the mass of the whole thing. Okay, thanks.